We'll look in a little more detail at continuous functions to real numbers. We'll visit them at various times, including, for example, distance functions are such functions, and we will use them for making a topological space into a metric space if we can, etc. But first, some elementary properties, the way we do in analysis, which will illustrate some things we just did. Okay, so here is the following. So right through, let's fix X a topological space. Now these are theorems you would expect from analysis. So suppose, indeed, in all three, suppose all parts, suppose f, g are functions from x to r, and these are continuous. F plus g is continuous. And f times g is continuous. And third, f by g is continuous, but not always, of course, provided g of x is not 0 for all x and x. And there are any number of variations of these, and they can all be proved in the same way. Indeed, even proving these is more or less an exercise, but we'll do this, we won't do the rest. By the way, if you wonder about difference, that is a combination of negation and so let me just make a remark. The cases a times f, and where this is a constant, so this is in real numbers, and f minus g, or rather I'll just say f minus g, etc. These follow from the above. In the case of a times x, you don't even need the x by composition. For example, if you want to know why multiplying by a is a constant, well, this is just applying the function f and then the function from r to r, which is multiplication by a. And we know that our usual epsilon delta continuity works for 8 functions from r to r, and hence this is continuous. Similarly, indeed, as a special case, the negation of a function is continuous, and so when you combine that with sum, you see this is continuous, etc. So linear combinations are continuous once you know this. Okay. Well, okay. So let's look at the proofs. We look at proofs of A and B. C is going to be similar, and mostly this will be recalling analysis proofs, but it will also be an exercise in using bases. Okay. So we prove continuity at all points for all x in x. So we use the fact that we have local continuity using the basis, and indeed not the basis even, but the neighborhood basis set of all balls around x of radius r, such for all so n at a point neighborhood of x is the set of all such things such that r is greater than 0. Okay, but we use this for x in r, so for real numbers we use this. And neighborhood basis of all neighborhoods for x. Okay, so what this means is that if I have a neighborhood, so here is, well, the squiggle, let's now say this is x, this is r, and I have a point little x, and I have its image f of x, and I take a neighborhood basis element, I have to find a set that goes into this, and this has to be in the neighborhood basis, but that's no constraint at all. All you need is it has to be open and containing little x. Okay, and we'll use this both for hypothesis that f and g are continuous and for the conclusion. Okay, so now consider, or rather let's first fix x. Okay. We'll do the usual variant of the usual, let epsilon be greater than 0 be given, and consider the neighborhood of size epsilon of f of x, epsilon greater than 0. So fix x in x and you consider this neighborhood, which is epsilon of f of x, epsilon greater than 0. Okay, so this is the set, and what we want to find is, oh, I'm sorry, it's not f, but we want to show for f plus g of x. We find v contained in x, so x in v open such that f of v is contained in this ball. Is contained in, oh, I'm sorry, I wrote n epsilon, it's of course b epsilon. And to clarify, this is f plus g of x, that's f of x plus g of x, b epsilon contained in b epsilon of f plus g of x. Okay, and I have to construct this v, we have to construct this v, and we will do it as usual by constructing neighborhoods corresponding to f and g with epsilon by 2 as replacing epsilon, namely, so as f and g are continuous, there exists wf and wg open such that x belongs to wf and x belongs to wg. Well, I better clarify, these are both in x. Open is open where? X is in wf, x is in wg, such that, so f of wf is contained in the ball of radius epsilon by 2 of f of x, and g of wf is contained in the ball of radius wg is contained in the ball of radius epsilon by 2 of g of x. Okay, so then what do we know? Well, what we know, that is, okay, so let v be the intersections of these two sets, wf intersection wg. Then if I have another point x prime belongs to v, implies that f of x prime is in this ball, mod of f, so which means belongs here, which means that this is less than epsilon by 2, and mod of g of x prime minus g of x is less than epsilon by 2, which implies, by usual use of triangle inequality, mod of f plus g of x prime minus f plus g of x, this is less than epsilon by adding these two quantities together, that is f of plus g of x prime is contained in that ball of radius epsilon of f plus g of x. Now x prime was arbitrary, thus f of v, f plus g of v is contained in this ball g of x, and we can also see that x belongs to V. By construction, it belongs to both of these, and V is open because it's the intersection of two open sets as required. So this is our usual analysis proof, simply translated a little bit. We use the fact that we can use, we didn't have to do any extra work because we have sort of encapsulated some simple facts into saying we can use neighborhood basis. And we didn't use it for the domain, we used the sort of trivial neighborhood basis for the domain, which is all open sets containing a point from which are, that is all neighborhoods form the neighborhood basis. So there was no constraint there and nothing extra there either. But on the real number side, we only had to prove this for the neighborhood basis. How about the product? For the product, we can take an even more refined neighborhood basis. So for B, which is the product case, which we'll prove later, observe that neighborhood basis is given by an x of, well, an x, the neighborhood system at the point x, is the set of all balls around x of radius r such that 0 is less than r is less than 1, say. There is small enough balls, in fact I could fix any eta, and balls of radius less than eta also form a neighborhood basis. So we need to prove and only for these, and we can use for one neighborhood basis and prove for another also. We won't have to do that. Okay. So with this background, we can prove B relatively easily. Okay, so proof of B. So that is, we are looking at f times g of x. Okay. So observe, if I look at f times g of x prime, this is the usual analysis trick, minus f times g of x. This can be broken up as by adding and subtracting a hybrid terms. Okay, so better to write this out explicitly as f of x prime times g of x prime. And then I subtract and add a hybrid term, one which has f of x prime again still, times g of x, plus f of x prime times g of x, minus f of x times g of x. And we group these together, so we have f of x prime times g of x prime minus g of x, plus the second term will be g of x into f of x prime minus f of x. And the usual analysis trick that we'll use, this was really the trick. The idea beyond this point is this is small and this is small if x prime is close to x, and this can also be bounded. Okay, so this is less than or equal to the difference between these two and x. So that's why we chose that 1 as a set. Okay, so so what do we want to do? Fix epsilon in between 0 and 1 and consider. Okay, so first of all, let's fix x in x. X in x. Then I'll fix this and consider b epsilon of f times g of x. Okay, that is, this is a basic neighborhood. Of f of x. And well, we would like to divide these two parts by 2, but there's an additional g of x, and g of x could be 0, so we want to pad that up. And this additional f of x prime, this could be bigger than f of x, for example, or smaller, so it could increase the number even more by having f of x prime instead of f of x. So we'll control these things. Okay, so it's in 0, 1, so f of x prime is not too far from f of x. So we'll control these things by saying, by continuity of f and g. Okay, so there exist WF, WG neighborhoods of X such that, well, f of WF is contained in the ball of radius epsilon by 2 into, well, let's take the opposite, 1 plus g of X. This is a constant. We are just taking this ball of radius epsilon. My notation has switched things. Ball, which is good because ball around f times g of X of radius. So, I'm sorry, not f times g of X, just f of X. So f continuity of f. So ball of radius around f of X of epsilon times divided by 2 times 1 plus g of X, and f of, sorry, not f but this time, but g of WG. This is contained in the ball around g of X of radius epsilon by 2 into 1 plus f of X. Okay. Fine, and you let V be equal to WF intersection WG. Okay, now epsilon is less than 1. So since epsilon is less than 1 and this quantity is even smaller, we have 2 into 1 plus epsilon. So observe that x prime in V implies that f of x prime is contained in this ball. So mod of f of x prime minus f of x is less than 1. Okay. So which implies that f of mod of f prime f of x prime is less than mod of f of x plus 1. So I should correct myself here. You take the absolute values here. So we have controlled this quantity here. Okay. So therefore, f times g of x prime minus f times g of x is less than or equal to, using these equations, as mod of f of x prime times mod of g of x prime minus g of x, which is a quantity that's small, plus mod of g of x, which we have controlled, times f of x prime minus f of x. So we have a mod of f of x prime minus f of x. And this in turn is less than, we have controlled all of these quantities. F of x prime is less than 1 plus mod f of x. Okay, and this quantity g of x prime minus g of x, well, since the image of WG which contains V under the map G is contained in this ball. So the ball of radius epsilon by 1 plus 2 into 1 plus mod f of x around g of x, that means this difference is less than epsilon by 2 into 1 plus mod f of x. And the other term plus mod g of x, and this one is easier, this is 2 into epsilon of 1 plus mod g of x, and which is in turn less than, the first term is less than or equal to epsilon by 2, and the second term is less than epsilon by 2, strictly less. So this is, well, the last thing is equal to epsilon. So what we have shown is that, so thus I will just write it to sort of connect with the definition. F times g, if I look at f times g acting on V, this is contained in the ball of radius epsilon around f times g of x. So given any such basic neighborhood, we have found the open set which is containing x, so basic neighborhood of x, so that the image of, except my notation is upside down, ball around f times g of x of radius epsilon. So given any such basic neighborhood, we can find a v so that this product function acting on v goes into this. Okay, quotient, again you have to do the same kind of things as analysis, except that it's positive, so you have to make it definitely positive in a neighborhood and work a little bit. It's not that it's trivial, but there is no new idea beyond what you have done in your analysis. So one variable analysis. So we have gathered together some useful results about which let us build continuous functions to real numbers. We will soon enough consider a concrete case of this, which is the distance functions, and we'll also consider an abstract property, coarse and fine topology, which lets us deduce what topology to have on spaces. These two are kind of intertwined things, these constructions of functions and these properties of spaces.